This climate graph for New York shows us temperature averages over the last 30 years for each month of the year. It allows us to see how temperatures vary across the year and the seasons. The horizontal or x-axis indicates the month of the year. The vertical or y-axes show temperature. So on the left-hand side you've got temperature in Celsius, which is the metric system and is the more common scientific way of recording temperature. And on the right side you have Fahrenheit, which is what we're typically used to in the US to describe temperature. So when we look at the graph, the yellow or orange line on here indicates the average highs that we expect for each month of the year, meaning the average high on any given day in that month of that year. So when we look at September, for example, we can see here that in September the average high temperature is 24 degrees Celsius or 75 degrees Fahrenheit. This is the warmest we typically expect September to be on average. The green line shows average low temperatures, the coldest it typically gets during the month. So for each month of the year, when we look at the average low temperature for September, we see that it's about 16 degrees Celsius or about 60 degrees Fahrenheit. This is the coldest we typically expect September to be. In contrast to the average high, the red line shows the hottest temperatures that have occurred in each month. So September has hit a record high of almost 40 degrees Celsius or 105 degrees Fahrenheit. So we know that it can get that hot in September, even if it's not common. The blue line shows record low temperatures, and so we know that September has gotten as cold as 6 degrees Celsius or 43 degrees Fahrenheit, which means we know again that it can get that cold even if it's not that common. So between the red and blue lines, between those extremes, we essentially see the range of possible temperatures in New York for September. You've read that air pressure is essentially caused by the weight of the air above our heads. So if we go up in altitude, there's less air above our heads, which means there's less air pressure. So this graph shows how atmospheric air pressure changes with altitude. The vertical or y-axes show altitude in two different measurements or units of distance or altitude. On the left-hand side you see that you have altitude measured in kilometers above the surface, and on the right-hand side you see altitude measured in miles above the surface. You can see that the top of Mount Everest is about 9 kilometers or so, or about 5.5 miles in altitude. The horizontal or x-axis shows air pressure in units of millibars. That's how we measure air pressure. So you read the x-axis relative to the red line. So if we look at the red line and we start at the surface of the Earth, the air pressure at that point on the x-axis is 1,000 millibars. As you follow the red line up, you see that air pressure drops with altitude. So by the time that you reach the top of Mount Everest, which is at an altitude of about 9 kilometers, the air pressure has dropped from 1,000 millibars where we started to 314 millibars at that point, at that altitude. So if we subtract 314 millibars from 1,000 millibars, we can say that the air pressure has dropped by 686 millibars between the surface and 9 kilometers of altitude. Air pressure is not the only thing that changes with altitude. We've determined that air temperature also varies with altitude, although it's actually a little more complex. So looking at this graph shows the thermal structure of the atmosphere at different altitudes. So the horizontal or y-axes show altitude or height in kilometers on the left-hand side and in miles on the right-hand side. On the x-axis, we see temperature indicated in Celsius on the top part of the temperature scale, and then in Fahrenheit in the bottom half of the temperature scale. So we read that x-axis or temperature relative to the red line. So if we start at the surface of the Earth on the red line, we see that the temperature is about 19 degrees Celsius or 66 degrees Fahrenheit. As we follow the red line and move up in altitude to the top of Mount Everest again, we're at about 9 kilometers of height, as you might recall. The temperature drops to about minus 45 degrees Celsius or about minus 50 degrees Fahrenheit. Once we get above 10 kilometers in height, though, we hit the tropopause, or the boundary between the troposphere and the stratosphere, and where the temperature actually begins to rise with an increase in altitude. although the atmosphere is so thin in the stratosphere that you would probably need a spacesuit to survive there. It turns out that the tropopause, or the boundary between the troposphere and the stratosphere, can be found at different heights or altitudes, depending on where in the Earth you are. If you're at a lower latitude, like in the tropics or near the equator, the troposphere is actually thicker and rises to a higher altitude. As we move to the middle latitudes, such as in Massachusetts, the height of the tropopause becomes lower as the thickness of the atmosphere declines. At the highest latitudes, at either the North or South Pole, the troposphere is much thinner, and the height of the tropopause is still lower there too. This graph shows the altitude of the tropopause in different regions of the Earth, as well as how temperature decreases with altitude in those different regions. So the vertical or y-axis shows altitude in kilometers. The horizontal or x-axis shows temperature in Celsius. Each colored line represents a different region. So, for example, the green line represents the atmosphere above the middle latitudes, which definitely includes Massachusetts, but actually includes an area of the continental U.S. Starting at the surface of the Earth with the green line in the middle latitudes, the temperature is about 16 degrees Celsius. Following the green line up, we see that temperature decreases with altitude. At about 11 kilometers of altitude, the temperature is about minus 52 degrees Celsius. It's pretty cold. And that's the lowest temperature it will reach before it begins to rise again. So this low temperature point represents the middle latitude tropopause, essentially the ceiling of the troposphere and the boundary before you start to enter the stratosphere. So looking at the other lines, you can see that how temperature declines at different rates depending on where you are. And more importantly, in this case, you can see how the tropopause occurs at different altitudes, higher in the tropical latitudes where the troposphere is thicker, and lower in the polar latitudes where the atmosphere or the troposphere is thinner.